So I believe everyone is convinced that designing a good crypto system is a very complex process. An even more complex process is to design a good crypto system that eventually gets used by people. So in the very simple scenario, the simple case, we have a designer, a cryptographer, who designs a crypto system with a well-defined key space, large key space. This design hopefully gets published in a very well-known cryptography. Hopefully, this design is going to survive other cryptographers' scrutiny for a long period of time, months, maybe years. And as I said, eventually this crypto system is going to be used massively by users, possibly by some software, allowing every user to instantiate, to obtain a keyed crypto system by choosing a key, and then the keyed crypto system can be used to encrypt messages, for example. So even in this very simple scenario, something has to happen in the middle here. And since we are at AWACS, this thing today is a standardization process. So this is a very simple picture, okay? It's very abstract, very simple. And as you can imagine, not every crypto system fits this very simplistic model. But there are a few examples which fit this. So take RSA, for example. When using RSA, when you have fixed the modular size, there is no complex parameters you have to choose. Of course, textbook RSA is insecure. You should use it with a proper padding scheme, like, for example, RSA or AEP. So RSA OAP, the OAP padding scheme was developed by Baignères and Rogawi in 1995, and then it was standardized, and it took about 3 years to standardize OAP. So I don't know much about the standardization process. I know a bit more now, but it took 3 years, which is quite a long time. So many other crypto systems don't fit this simplistic model. So in practice, the figure should look like this. So let's see what we did change here. So first, the designer crypto system does not only come with a well-specified set of acceptable keys, it also comes with an acceptable set of acceptable parameters, right? This fact complexifies the work required from the standardizer a lot, because she typically has to choose fixed parameters in order to obtain what I call an instantiated crypto system with a fixed set of parameters in order to make this crypto system practical for end users. So at first sight, it might seem that this is a simple task, okay? After all, a well-known designer defined a set of so-called acceptable parameters. So picking one parameter in this set should make it acceptable by definition, right? Well, no, of course not. So the reason is that an arbitrary looking choice from the standardizer might not be arbitrary at all, as we have understood from the previous discussion. So this may lead to potential trapdoor in the instantiated crypto system, that's the crypto system that people will use in the end. So for example, just a small example, assume that the set of possible parameters are all the generators of an elliptic curve of prime order. So this leaves a huge number of presumably equally valuable choices for the standardizer, right? At this point, a honest standardizer could simply choose one of these generators uniformly at random. It's very simple. What could a dishonest standardizer do? Well, it could choose some secret generator J prime and then compute the public generator J by computing this generator as some K times J prime, right? So the knowledge of a discrete logarithm of J, some basis, might provide the standardizer with a trapdoor, making the final instantiated crypto system completely insecure with respect to this standardizer. One should note here in this trivial example that for an external reviewer, it's impossible to distinguish between the J drawn by the honest standardizer from the J drawn by the dishonest standardizer because both distributions are identical. So in a nutshell, this is exactly what happened with the infamous dual elliptic curve deterministic bit random generator. So the sole fact that there may exist dishonest standardizer implies that the method suggested for the honest standardizer is doomed. Indeed, how can this honest standardizer prove in the end that she did not actually know some discrete logarithm of j in some basis? Well, actually, she can't prove it, right? So the trivial method is not enough. So this brings us to the main topic of this talk, which is rigidity of cryptographic parameters. So we define rigidity as a subjective characterization of the parameter generation process of a well-designed crypto system. And this rigidity represents the level of trust one has in the security of the instantiated crypto system. Okay, so that's my own definition of what it is. So on the SafeCurves website, Dan distinguishes between 4 levels of rigidity, going from fully rigid, which is good, then somewhat rigid, manipulatable, and trivially manipulated, which is very bad, of course. So let's have a very quick look at a scale going from fully rigid down to trivially manipulatable. So on this scale, sorry, we can say that, well, I would say that any standard that did not have to make any parameter choice during the standardization process is fully rigid. So RSA OAP is such one example. So another example of fully rigid crypto system is curve, I don't know how to pronounce it in English, but curve 25519, where all the choices of the parameters were chosen to achieve optimal efficiency. A slightly less rigid example is the AES, for example. Indeed, during the design process, a few unjustified choices were made. For example, as far as I know, there is no justification for the field representation, nor for the affine transformation of the substitution box. Of course, I did not say that this introduced any trap in the AES. In my point of view, it's very unlikely that this allows to introduce any trap, but anyway. And of course, at the very bottom, we have our good old dual CDRBG. So, as we have just seen, not all standards are fully rigid, right? So let's see when things can go wrong. So typically at design time, at the very beginning of the process, the designer comes up with a crypto system that accepts a huge set of parameters. That's what we call the full parameter space here. Then the cryptographer, the designer, is going to try to break her own scheme, okay? As a result, she will come up with a list of attacks and eventually restrict this set of parameters. And at this point, we have a smaller set of acceptable parameters, which we call the secure parameter space. So at this point, the cipher is secure for a few weeks or months. So other cryptanalysts, of course, are going to find new attacks, restricting the acceptable parameter set even more. And now we have the really secure parameter space, okay, which is smaller. At this point, if you want your cipher to be actually used in practice, you will have to talk to practitioners. And practitioners are going to say, okay, I want your cipher to be fast. And there are these specific choices of the parameters which allow me to have a good implementation of your cipher. So at this point, you will have a new set of parameters, even smaller, which I call the fast and really secure parameter space. Okay. So now, that's the acceptable parameter space. And now you can be in either of these two situations. So the first situation is the simple one. In the simple case, you have a single parameter left, like in Bernstein curve, for example. In other cases, you still have a lot of parameters to choose from. And that's the complex case. This is where things can get difficult, okay? So in the rest of this talk, I will explore how a honest standardizer can deal with this problem, how a honest standardizer can instantiate a fully rigid crypto system when she has a lot of parameters to choose from, okay? And as a running example, I will stick with elliptic curve parameter selection. So let's go back to the figure we had at the very beginning and see how we can do this. So we saw that this process, as it is represented here, is not sufficient. Indeed, this is exactly the process that was followed during the generation, the standardization, sorry, of duality. So clearly this is not enough because this allows a lot of unjustified choices. Strangely enough, this is also the process that was followed by the French Network and Information Security Agency to standardize this elliptic curve here. Don't use it. Okay, some standards, how we have seen, have unjustified choices. Some standards have chosen to avoid unjustified choices. This is, for example, the case of the standard standardizing P256. In their case, what they did, to convince that the curve was really generated at random, they chose a seed, and they used this seed to feed a filtering function. What I call a filtering function is a deterministic procedure that maps the set of seed onto the set of acceptable parameters, okay, a balanced function. So they chose a seed, here it is, they fed the filtering function, and this generated the parameters. So is this enough? Well, might not be. Assume that the standardizer is not honest, and assume that the standardizer knows a not too small subset of the acceptable parameters for which he knows an attack, an obviously unpublished attack, okay? Assume that this attack exists and that it is known to the standardizer, and assume that this subset is not too small. Well, in that case, breaking security is trivial, because the standardizer can simply iterate through many seeds, each time passing the seed to the filtering function, look at the obtained parameter, and if the parameter falls into this small subset, then he's done. Actually, we don't know if this is what happened, but the problem is that we have no proof that this is not what happened. Okay. So this fact was obviously acknowledged by the Brainpool team, who decided not to use a random-looking seed. Okay, they used a so-called nothing up my sleeve number. So the number they use, if I'm correct, is the Euler number, right? And using such a number in cryptography is quite common. Okay, there are a lot of standards who used or even designed who use such numbers, and these numbers are supposed to put the final design or standard above all suspicion of manipulation. So as Dan said, okay, spoiled my slide, this is not enough, okay? So I'm not going to go back on the whole story, but this is not enough, and it's not, well, as Dan showed in the paper, it's not it's not really complicated to bypass this trick here. The reason is that you can wonder why x1, why not the sign function like in MD5, why didn't you use 1 over pi like in area, and so on. Okay, so we have to do better than this. Okay, first, let's have a look at the filtering function. So the filtering function obviously should be chosen before the seed is chosen or drawn. Okay, why so? Because otherwise, given any seed, you could design the filtering function to obtain any kind of parameter you will want to obtain. Okay? So you should not publish the seed and the filtering function at the same time. You should definitely publish the filtering function beforehand, right? And actually, since you need to design the filtering function, and since you have a designer on the top left, maybe you could let the designer just design this filtering function, okay? He knows the design. I'm sure he's going to be able to provide a good filtering function. Okay. Last but not least, on the filtering function, I believe that a filtering function should not be a pen and paper description. It should be actual code, Python code. As you have seen on the previous slides, it can fit on one slide, so it's not a very hard work, but I mean, it should be code that actually anybody can execute. So, okay. So now the standardizer only has to generate a seed in a trustworthy way, okay? She can do so by making this generation publicly verifiable. And generating a a seed in a trustworthy way, in a publicly verifiable way, can be done by what we called in a paper by a publicly verifiable RNG, or PVR for short. So what is a PVR? So a PVR is a random number generator, which is very hard to manipulate, publicly observable, which means that all the sample generated by this RNG are public, and it must be archived, so that anyone in the future can pick a past date and get the result of this PVR back. So assume that we know how to construct such a PVR. Assume that we have one at hand. How can we use this in the scheme that we had on the previous slide? So I'm going to go to describe the process from the very beginning. So first, as I said, we have a designer, that would be you, designing a good crypto system, defining good security criteria, inducing a parameter space, and providing code for a filtering function, okay? At some time t0, this designer should timestamp this design, okay? So that at any time t after t0, anyone can check that the design has not changed since t0, okay? At some time t1 after, a standardizer is going to choose two things. He's going to choose a PVR, well-defined PVR, and two dates in the future, T3 and T3 prime. So T3 is the date in the future corresponding at the time at which you are going to collect entropy from the PVR, and T3 prime is the time at which you will stop to collect entropy from the PVR. Then the standardizer is going to commit on these choices as well as on the design, the timestamp design from the designer. Okay? It is very important here that this time T2 lies before T3, right? So at this point, after T3 prime, so that after the generation process, we have a seed, and it's trustworthy. And actually, anybody can use the filtering function that was timestamped with the design, can use this seed, which is public, to instantiate the parameters of the crypto system. And once we have the parameters, we are almost done. This is the big picture. Okay. This works, I think it works, as long as we have a good PVR. The problem is that finding a good PVR is very hard. So remember that we want the PVR to be very hard to manipulate, publicly observable, and archived, all right? So here are a few, the first example that could come to your mind. So classical cryptographic RNGs are not enough because they are not publicly observable. Websites like random.org are trivially manipulatable. Stock market prices are certainly manipulatable if you have money. Weather data is somewhat predictable. If you live in Belgium, you know that it's going to rain. There was a proposal by Bono, Clark, and Goldfeder based on the Bitcoin blockchain. It's not clear whether to me, if the Bitcoin blockchain is manipulatable or not. There is an interesting paper by Piero and Veselowski on that matter on the ePrint. And in many cases, it's very hard to measure the exact entropy of the PVR. Nevertheless, two recent constructions were introduced very recently, one by Lenstra and Veselowski. Their solution is based on Twitter, on a very smart slow hash function, and on a webcam. And one other proposal was introduced by a crypto expert. And our solution is based on national lotteries from around the world. So I'm going to say a few words on these two PVRs so that you understand how they work. So first on the Lenstra-Veselowski PVR. So as I said, at time T2, they commit on two time in the future, T3 and T3 primes. What happened at T3? So at T3, they start to collect entropy from Twitter. They look at tweets which have this special hashtag here. So that's just the name of the curve they want to generate. At T3 prime, a lot of things happen. So first, as I said, they stop to collect entropy. This entropy gives them a seed, a first seed, S0, okay? They're not done yet. They have to take a quickly, they take a picture of the EPFL parking lot. Well, it could be any place on the planet, but in their case, since they are at EPFL, they take a picture of the parking lot. And this gives them another seed, S1. Sorry. Then they instantly publish a commitment on a hash of these two values. Okay? It is very important that these three steps here occur in a very short period of time. And then after that, they are going to start to compute a very slow hash of the value on which they committed. Eventually, this will give them the seed they are looking for, the trustworthy seed. And they also have a fast verification procedure. So just a word on our proposal. At time T2, we publish an ordered list of future lotteries, where each line is one well-defined lottery, a well-specified date and time at which a draw is supposed to occur. So we published such a list, and we published a seed extractor, that's code, a piece of code, Python code in that case, which turns an ordered list of results into a seed. Okay, we published this. And after that, our work is almost done, because at time T3, we only have to publish the draw results, which are available by other means, and we compute the seed. That's the least that we could do. But anyone could actually do this work afterwards. So at time T4, anybody can check the results and regenerate the seed. So there are pros and cons in both solutions. I'm going to scan quickly through that. So in their case, the process can be made fully automated. They actually, today, they generate several curves every day. It uses Twitter, so anyone can participate, which is nice. They use Twitter, and tweet can be deleted. And what if you generate a curve using a lot of tweets, and one of these tweets get deleted? Well, you can't verify the generation process anymore, which is bad. It's hard to predict or to measure entropy. What if nobody cares about your curve? Okay, so maybe nobody's going to tweet. It's non-trivial. There are non-trivial tasks that can only be performed by the standardizer, like the shot with the webcam. In our case, the process is completely decentralized. We use lotteries all around the world. The entropy is easy to quantify. Once the draw list is committed, we cannot go back. I mean, we are committed, and the process cannot be stopped because anyone can compute the rest of the process. But the bad thing is that lotteries have a very, very bad reputation. What can I do? So, conclusion. So when generating parameters, standardizers should do it in a fully rigid way. This can be done for any cryptographic scheme, not only elliptic curve, but any cryptographic scheme, provided that you have a convincing PVR. So the problem is that they are hard to find. Two PVR constructions that have been proposed. I personally believe that they are both convincing, but I'm aware that this feeling is not shared by everyone, making these PVRs imperfect. In that sense, no PVR probably will ever be perfect. At least, proposals like these set a minimum level of requirement for future standards. And now, well, I was supposed to say thank you now, but yesterday I had dinner with a bunch of cryptographers. We have too many beers, and we start to discuss about this subject. And I learned something that I'm going to share with you now. So I'm not sure. This is new to you. It might be to some of you. So anyway, I'm going to say it. I didn't have time to check the details, so you are grown-ups. Please check the details. I don't know if this is true or not, but anyway, okay. To make it simple, there might be another dual EC DRBG out there. So if you look at this standard here, so I try to have a look, but as you know, they are not free, so I don't have it. Don't have the real standard. But I found on the internet yesterday night on my iPhone, I found a draft, a 2004 draft, and I looked at section 10.3.3, where you will find, so that's the same standard as a dual EC DRBG. So you will find another DRBG, which is called Mikali-Schnorr, which looks, well, it's similar to Bloom-Schub, except that you don't square things. You compute x at the power e modulo n, where n is an RSA modulus. Okay? I'm sure you see it coming. So in section 10.3333, about the selection of the Michaelis-Schnorr parameters, you can read: the application may request a private modulus, or it may use the default modulus of the appropriate size as given in Annex A2. So the implementation shall permit either you, so you have to use the modulus that you can find in section A2. So needless to say, you won't find the primes. You will find the modulus of the appropriate size. So this is definitely an example of a non-fully rigid parameter selection. Thank you very much.
Okay, are there any questions for Thomas? Yes?
Yeah, so one thing I was going to suggest, first of all, is there any reason you couldn't incorporate the sloth hash function into your process? Since that would make it harder for an attacker. The sloth is the slow hash function, the Lenstradal hash function, and that would then make it harder for somebody who wanted to tamper with that last lottery, because they would have to spend more computing time to know what to do, right?
Yeah, actually, when I prepared the slide, I looked at both solutions and I realized how similar they were, because I mean, you can see it when you see the whole figure there. So obviously, we have the same problem as they have when you have your list of lotteries. The last draws are very, they are sensitive because they know the result of the previous draw. So you should be very careful about the last draw. So we have a technique. I don't know how to say it in English. Well, there is no security proof. It's done with hands, and that's how we would say in French. So we have a technique that we call the lone bits. That means that once we have gathered enough entropy at the end, we continue to consider draws, but only keep 1 bit of entropy for every draw, and we take care of choosing draws coming from lotteries in different countries. But I mean, that's not cryptography. Okay, it's just we did what we could, okay? Obviously, we could have used a slow hash function, but we just wanted to try to find another solution. But definitely, another solution that you could just remove this lone bits thing that we have in the paper and replace it using the slow hash function.
A couple other suggestions I wanted to make for this, and maybe this is already something you're doing. You talked about including a commitment for having the designers include a commitment and then publish the commitment to the exact procedure that's being used, the filtering function. It seems like you should just include a hash of the full specification as part of your seed. That way there's no way for that specification to change without changing the outcome.
Yes, indeed.
And the last thing was, it might make sense if the standardizer does not control the lottery, right? Since you as the standardizer don't control the lottery, and probably it's hard to find overlap between people who control the national lottery and people who are writing the standards, it might make sense for the standardizer or the submitter or even several people to provide a commitment to a random number and then open that at the end of the time period. That would also then give you some extra verification that at least the designer couldn't be cooked because some other person took over the lottery.
We have taken into account this suggestion. Actually, in the paper we suggest that somebody could commit on some value and reveal it at the end. But again, this is a point of failure, all right? This, like any lottery. So in the end, maybe this will sound more convincing to somebody, but maybe not. So it's difficult to come up with the great idea that will convince everyone. But thank you.
So you say that RSA-OEP is an example of a standard with full rigidity, but RSA-OEP heavily relies on some MGF function, which is not a very good example of full rigidity, right?
Thank you, Serge. Okay, you're right, as always. I was just trying to find a good example and just ruined it. Okay, here was PhD advisor, so he's having fun now.
Concerning your bonus slide on the Michaelis-Schnorr generator, I just wanted to point out that a few of us in the community have known about this generator for probably 18 months or 2 years now.
Oh, okay, sorry.
But I don't want to raise the auditing bar on you, to use Dan's phrase, but I think it's a really interesting research question and quite a hard question. Given some output from this generator and knowledge of the prime factorization, how do you recover the state or previous outputs or future outputs? I don't think we have to solve that problem in order to get rid of this generator, but I think it's an interesting research question.
Yeah, indeed, I'm sorry, I forgot to mention that. Of course, I have no idea how you could predict a generator. It's not as trivial as in the dual C case. Okay, so.
And it's still open, right? I mean, we don't know how to do that.
Yeah.
Even if you control the primes,
Yeah,
yeah.
yeah.
It's not clear
Yeah.
that
Yes.
But that shouldn't be a requirement for getting rid of it, if I understand.
Definitely.
Yeah,
Sure.
As a nitpick, I know that's not in the ANSI. It's not in the ANSI document, and it's not in any NIST standards. I believe Macaulay-Schnorr may have been in some ISO standards, but I wasn't involved in the ISO process.
okay.
But you might want to check that. But it's not in it's not in ANSI X9.
Okay, okay.
It's in an ISO standard, and
Yes.
the modulus came from NSA.
It's in the 18031 standard, the ISO standard about deterministic random bit generation. Yeah, definitely. All right. I think we should move on to the next session and maybe keep, our thoughts about rigidity and these kind of issues for the later panel discussion.